You know that feeling when you try just one potato chip and you instantly know if the whole bag is going to be good? Well, that's sampling in a nutshell. Today, we're diving into how scientists use that exact same idea, but, with much higher stakes. We're going to go from chips to entire populations, and you'll see how a tiny taste can actually reveal the truth about the whole picture. Let's get into it.
Seriously, think about it for a second. You eat one chip, and bam, you've made up your mind about the entire bag. That little chip, that's your sample. And the whole bag, of course, is the population. You're making a pretty big call based on a really small piece of information. And that's exactly what we're going to unpack today.
But here's the thing. There is a huge difference between our casual taste test and what scientists do. Our everyday sampling is, well, it's all about what's easy, what's convenient. Scientific sampling, on the other hand, is a super careful process. It's designed to be as accurate and unbiased as possible. And it has to be, because it's the foundation for research that can literally change how we see the world.
Okay, so how do we make that jump from a gut feeling about a chip to a rock-solid scientific conclusion? It all starts with setting some ground rules. Before we can even begin to think about picking our sample, there are a few key ideas that every researcher has to get right. First things first, the population. And this isn't just about people. A population could be anything, really. It could be all the students at a university, every car that rolled off the assembly line last year, or even every documented case of a specific illness. It's the entire group we want to know something about. Now, trying to study a whole population is usually impossible, or at the very least, just not practical. Imagine trying to talk to every single person in a country. So instead, we select a sample. This is just a smaller, more manageable piece of that population. By studying this sample, we can then make some really smart guesses about the whole group.
And this brings us to the holy grail, the ultimate goal, getting a representative sample. What this means is that our small group should be like a perfect miniature version of the larger population. It needs to reflect all its important characteristics. So if your population is 50% men and 50% women, your sample should be too. It has to mirror the real thing.
So this all comes down to two big principles. The first is similarity. Think about it. If your population is really uniform, say a batch of lab rats that are all genetically identical, you can get away with a smaller sample. But if it's super diverse, like all the voters in the United States, you're going to need a much bigger one to capture all that variety. The second principle is precision. You have to be crystal clear about who or what is in your population to make sure your sample is actually representative and not biased.
All right, with those rules in our back pocket, let's talk about the gold standard of scientific sampling. It's called probability sampling, and it's all about one thing: fairness.
The main idea here is simple, but it's incredibly powerful. Every single person or element in the population has to have a fair shot at being included in the sample. This is what separates rigorous, trustworthy science from just a biased guess. This quote just nails it. An equal chance and a known non-zero chance. That means nobody is left out on purpose and everybody has the exact same odds of being picked. This is the mathematical backbone of unbiased sampling. And because it's so focused on fairness, probability sampling is absolutely the go-to method whenever researchers want their findings to apply to a bigger group. If you're confident your sample is a mirror of the population, then you can be way more confident about what your results mean for everybody. So let's get into the nitty-gritty. We'll start with the most basic, the purest form of probability sampling out there, the simple random sample. The process itself is surprisingly straightforward. First, you define your group. Second, you make a master list of every single member. Third, you decide how many people you need in your sample. Fourth, you give everyone on that list a unique number. And then, for the final step, you just select numbers completely at random. It's about as pure a form of selection as you can possibly get.
So how do researchers actually do this random selection? Well, it can be as simple as the lottery method. I mean, literally drawing names out of a hat. For a more old-school scientific approach, they might use these things called random number tables you'd find in a stats textbook. But let's be real. Today, it's almost always a computer program generating a totally random list of numbers.
Now, simple random sampling is great for sure, but it can be a little clunky, especially if you have a huge population. So researchers came up with a more efficient but still totally valid alternative. Let's check out systematic sampling.
The big idea here is, Well, it's to use a system. Instead of picking numbers out of a hat one by one, you select people at a fixed regular interval. So, for example, you might decide to pick every 10th person that appears on your master list. The process is just 4 easy steps. You get your complete list, you figure out your sample size, and then you calculate what I like to call your magic number, the sampling interval, which we call K. Then all you do is pick a random starting point and select every kth person on the list from there.
Let's make this concrete with an example. Let's say there are 280 petrol stations in a directory. That's our whole population, N. And we want to sample 70 of them. That's our sample size, N. So we just divide N by N. 280 divided by 70 gives us a sampling interval, K, of 4.
Okay, so here's how it plays out. You'd randomly pick a starting number between 1 and 4. Let's say you pick the number 3. Your first selection would be the 3rd station on the list. Then you just keep adding forward to get your next ones. So you'd pick number 7, then number 11, then number 15, and on until you got your full sample of 70. It's way more efficient, and as long as that initial list was in a random order, it's just as unbiased.
So let's bring this all the way back around. We started with a potato chip, and now we're here calculating sampling intervals. Why does this jump from a casual guess to this methodical scientific approach? Why does it matter so much?
Well, here's the real power of it all. Scientific sampling gets our own human biases out of the equation. It's what allows a small study to confidently speak for a massive population. And this might sound crazy, but a well-chosen sample can sometimes give you an even more accurate picture than if you tried to survey every single person. At the end of the day, this is the bedrock of any poll, any study, any piece of research that you can actually trust. And that kind of leaves us with one final thought. Now that you know the difference between a random guess and a systematic selection, the next time you see a headline about a new poll or a big study, I hope you'll stop and ask yourself the most important question of all. How did they choose their sample? Thanks for tuning in.